Okay, how you guys doing today? What we're gonna be doing here is going through a static problem. This will be a 2D static problem that I'm gonna go with. And first things first, let me tell you about my sponsors really quick. They are, first of all, they're very nice people. They hired me to kind of put their name out there with their website, and the name of their website is contestcelebration.com. And what they do is they have contests, a picture based contest. It's theme based, so say 1 month they say, hey, take your best beach photo or your best zoo picture or something along those lines, and they give out a $500 prize every month. And they're starting up right now, but there's definitely been a lot of people going towards them, and they've had a few winners along the way. So that is contestcelebration.com. So check that out. And again, this is definitely a real contest. People do win this one, and you can contact them. They got their hours on the website there. And so anyway, they were gracious enough to pick me to start doing some tutoring. So I went to college. I have a degree in aerospace engineering. I also have a math minor. And one of the classes that I took that I noticed that there wasn't a whole lot of help for was statics. Now, some people, they view this class being really easy. Some people, they find it extremely difficult. And so I'm just here to maybe, see if I can help with that. I'm going to start off with the problem that, I'm trying to make this realistic so easier to relate to. Because I noticed whenever I was doing a lot of those problems, some of them were just a little outrageous. Like, I had a physics problem where problem statement says, hey, there's a whale in the ocean and we're going to pick it up with the crane and transport it, calculate the speed or angular momentum or something along those lines. And I remember thinking, why would they build all that infrastructure in the middle of the ocean just to have a crane? Or why would they pull a boat out that far with the crane on it? Wouldn't it have a net or something they could just pull the whale? But hey, that was just me. Maybe I'm too logical there. So anyway, this problem's setting up. Gonna have something hanging from these chains, and that this sign right here. This means a wall or a hard surface. It doesn't move. So our chain is gonna automatically, we know it's gonna be in tension, and that means that, let me draw this down here. That means that the force is gonna be pulling outward of the chain. Say this is my chain, whole thing. Yay, chain. Force is gonna be acting outward away from the center of mass, right? And we know chains can't be in compression because, well, you can't push anything with the chain. You can only pull, right? It'll get all jumbled if you try anyway. So enough of that. Now let's say that we have our chains, and that's a metal ring chain here at some angle, chain directly off to the side, and we'll put something hanging from it. Let's say somebody's trying to kidnap me and put me in a cage. I did something wrong, or they don't like the school I went to or something like that. So they want to devise something, some sort of structure here. So they could only afford certain types of chains, right? So let's just draw a quick cage here, put me in there. And by the way, my captors are going to be engineers. Definitely going to be engineers. So, kind of drawn through that one. So what we're gonna do here is we're gonna see what they can go with on this. So they haven't, these captors, they have a couple sets of cages, and we'll put me in there with the sad face, not crying, just sad. So let's draw some points here. We'll call this point A, we'll call this one B, and we'll call this point C. and for reference, I will draw a frame of reference. So I'll have my y direction going straight up, and x direction being to the right. So there's my problem. So these engineers, they don't have much money. They're probably still in college. Maybe it's their second year, don't know. So let's say that this chain here, maybe they bought it from some random company, that's not the same as this one. Let's say they got this chain in Senegal. We'll go with that. See if any geography nuts out there know where that is. Most people don't. But yeah, let's say they got this from Senegal. And this chain can exceed a tension force of, we'll go with, we'll go with 450 pounds. So the force in the chain link AB, right, cannot exceed 450 pounds. Let me see if I got that right. 450 pounds. Forgot my units. And this one, let's see, they got this one from, let me try and think of a country that some of you geography nuts out there might be not expecting. We will go with, how about Ghana? Yeah, we'll go with Ghana. So they bought this from Ghana. And we'll say that this one cannot exceed 480 pounds. Okay? 480 pounds. So the question is how much can this cage with me in it weigh? So we'll just say weight of the cage and me. How much can this weigh? What's the most amount of weight that can be here so that these chains won't break? Because if it breaks, I'll hop out. Engineers will be mad. They'll start plotting. They'll start plotting big time. They'll try to get me, and they'll run back into the same problem. So the first thing we got to do with this, well, if I'm in the cage, it's a good chance I'll be too sad. I won't be moving. So we know that from our Newton equation that the sum of all forces is equal to mass times acceleration, right? But in this case, nothing will be moving, right? I'll be asleep or too sad, so nothing will be moving. So the sum of all forces is going to equal to 0, right? Nothing's moving, so everything's in equilibrium. That's what we call that, equilibrium. Now, what you can see here, you want to draw a free body diagram. So you know that you have weight pulling down on this ring, pulling down on that metal ring. You have a force pulling in this direction from this chain AB, it's in tension, and a force going in this direction from chain AC. So now we want to see is we want to write the equations out and solve for how much the weight can be. So let's assume the maximum for this chain. Let's assume that the maximum amount of force that we can put on it is already on it, and go from there and see if we can get a weight. So first thing I'm going to do is I'm going to write the sum of all forces in the x direction, right? So I've already kind of defined where this goes, but I'm gonna write the equation out without. I'm gonna pretend like I don't know that it's in tension. So the sum, I'll draw a line here so there's no confusion. So the sum of all forces in the x direction is going to be equal to 0, correct? So if I rewrite that and I write out the sum of all forces, so I've the tension in chain AC, which we've denoted as force AC, is going to be it'll be equal to this force, this X component of the tension force in chain AB. So breaking down into its components. So the X component of this force right here in chain AB is going to be the magnitude of that tension times the cosine of the angle that's here. So we'll call this angle theta for now, and we'll say it's 30 degrees. We'll say this angle here is 30 degrees. Yeah, we'll go with that. So this is going to be equal to 0. Forgot my plus sign. So now we can plug and chug. We can plug in some numbers here. So first I want to assume that force AC is equal to 480 pounds. We're just gonna assume that that's what that force is equal to, right? And that's going to be 480 pounds in that direction. Why? Because chains are always in tension. So minus 480 pounds is what we're going to plug in. I'm just going to write that here so we don't forget. But a great technique for solving equations is to solving for something is to plug in your numbers after you've solved the equation for what you're looking for. And I'll show you how that works. So we're going to be looking for force AB, and I'm just going to rewrite the equation here. And we need to isolate force AB. So we're going to subtract force AC from both sides of the equation. It'll cancel out here, and it'll go to the other side of the equal sign as a negative force AC. And then we need to divide by cosine theta so that we can isolate force AB. Right? So let me get my trusty calculator out after I plug in some numbers. So we said we were going to assume that it's 480. Glad I wrote it because I almost forgot. I don't know how, it's right up there. So it's negative 480 pounds divided by the cosine of 30 degrees. So this is going to equal, let me grab my trusty calculator. Grab that really quick. So 480. Ooh. So this is gonna come out to be, ooh-wee. Make sure I got this right. This comes out to be 200. And sorry for the long wait, guys. My calculator actually ran out of batteries. But I'm pretty smart, and I used a well-known search engine to get this answer. So this comes out to about 277 pounds. So if you're an engineer, you know that there's a certain amount of decimal points, and then people soon after start to not care. And we can go with 6 figs here. So this isn't like a chemistry class or nothing. Me personally, I like to use exact numbers, but this comes out to 277.128129211. We're going to call that 277.128 pounds. Right? So this does satisfy the other constraint that we have. The force is less here, so we can go over here and I'll draw a squiggly line so we know we're dividing things up. And we can try to see what the weight would be if we have this as a force for the magnitude of force AB. So summing all the forces in the y direction will let me find what the max weight here will be using this constraint. So weight plus, and I'm going to assume that I don't know the direction of the weight's going, weight plus force of AB is going to be equal to 0. And this one's the one I'm looking for. Oh, sorry. Almost made a mistake. Weight plus the y component of force AB, so that's sine of angle theta. Sorry about that, guys. Is going to be equal to 0. So this one's pretty simple. You take this term, you subtract it from both sides, and you get, oh, it's not going to be a vector because we're already in the y component, so yeah. So the y is subcomponent of this. So weight is going to be equal to a minus force AB times sine of angle theta. And that will be equal to this 277.128 times sine of 30 degrees. And that equals, and this one won't take me nearly as long because I got everything situated. Sine degrees. So that equals a negative, and that's because we said we didn't know what direction it was going, a negative 273.811 pounds. Okay, so I'm not that heavy, and maybe they don't have enough materials for this cage, but if it's made out of wood or something, could hold me back for a little bit. So it's negative because of my sign convention. I had y going positive, and so that tells us the y component's going up. That's the way it should be. So now let's take the next case. Now let's go the other route and see if we can have more weight. So I'm gonna cover this up and I'll rewrite these equations because these equations are still gonna hold these right here. So let's see, force of AC plus the force of AB times cosine of angle theta, which is our 30 degrees, is equal to 0. And this is the sum of all forces in the x direction. And there's different ways to write this problem. Some people like to use like a vector notation and keep everything all in one equation. But I find that to be a little bit more difficult than it needs to be. So back to our problem. The sum of all forces in the y direction is going to be weight is equal to negative force AB times sine of angle theta. So what we want to do here, let's see, I'm going to go with this equation because there's a constraint on this one. So now I'm going to assume that force AB is equal to 450 pounds. I'm going to assume that's the tension. So now I got to solve for this. So I subtract this term from this side of the equation and subtract it from the 0. So I'll write that out this time just in case anyone was confused before. minus cosine theta minus cosine theta. And that will give you the equation for the force in AC. Let me cover this right on up. Right there. So that looks really good to me. So that's going to equal, force AC is equal to negative force AB times cosine theta. So that's equals 450 pounds times cosine of 30 degrees, which will give us, see, you know the answer is going to be in pounds. Let me grab my calculator. So it's 450 times cosine 30 degrees gives us about 70 pounds. So it comes out to 69.413. 69.413. And that is negative per our sign convention, and that makes sense. It is pulling this way. That's where tension goes. So that satisfies our constraints too. So now we know that either way our constraints are satisfied. So we need to find out what the max weight can be if we go this route, where we assume that force AB it's at its maximum, where it's 450 pounds. So let's move over to this equation where we sum all the forces in the y direction. So weight here is going to be equal to a negative, and we assume it's 450 pounds. 450 pounds times the sine of 30 degrees. Okay, and that'll give us what we're looking for. So 450, I'm plugging in my calculator now, times sine of 30 degrees and that is negative. It comes out to, that's a lot, 400, almost 445 pounds. So this is negative, remember, pointing down. So 444.614 pounds. And there you have it. So the maximum weight, we'll call that weight max, can be equal to, and this is a magnitude, right? Magnitude, that's the way you would denote a magnitude. If you were coming from vectors, let people know what you're talking about. It's going to be 444.614 pounds. So me, let's see, I weigh about, I'm not going to tell you my real weight. We're going to go with 170. So we can say I weigh 170, and they can build a cage that can weigh up to 274 pounds. So they could actually use a lot of material. And let's be real, it's not gonna hold me. But anyway, yep, that is your statics problem of the day. And once again, remember the website, Contest Celebration. Go there, create a profile, and see if you can win $500. Yeah. Alright guys, good luck with that homework.